Now, in this lecture, we will find out the length of line segment X using two different methods. In the drawing, we have a semicircle inside the quarter circle. Note that side AO equals to 6 units. AC is tangent to the semicircle at this point. And we want to find out the length of side AC that is actually equals to X. So we start with the first method, and we will define the point of tangency of tangent AC with this semicircle as point D, and we will define the center of this semicircle as point P. AO is the radius of the quarter circle because of the fact that it starts from the center of the quarter circle, that is to say from point O, and ends at point A, that is the point on the quarter circle itself. Therefore, AO is the radius of the quarter circle. For the same reason, OB is also the radius of the quarter circle, that is equal to 6 units. So here we can write down that OB equals to 6 units. But OB is not only the radius of the quarter circle, but it is also the diameter of the semicircle. So we know that the diameter of this semicircle equals to 6, and we also know that the diameter of any circle or semicircle is twice as large as the radius. So if the diameter equals to 6 units, then the radius of the semicircle will be half of it. That is to say, the radius will be equal to 3 units. So here OP is the radius of the semicircle because of the fact that it starts from the center of the semicircle, that is to say from point P, and ends at point O, that is a point on the semicircle itself. Therefore, OP is the radius of the semicircle, that is to say it is equal to 3 units. For the same reason, exactly, PB is also will be equal, will be the radius of this semicircle, that is to say it equals to 3 units. And we will join points P and D together by a straight line. Line segment PD starts from the center of the semicircle, that is to say from point P, and ends at point D, that is a point on the semicircle itself. Therefore, PD is the radius of the semicircle, that is to say it is equal to 3 units. And we also know that AOB is the quarter circle. Therefore, this angle must be equal to 90 degrees. Angle AOB equals to 90 degrees because of the fact that this is a quarter circle. This angle AOB must be equal to 90 degrees. Okay? And O is of course the center of the quarter circle. In the next step, we'll join points A and P together by a straight line. And here the right triangle APO is congruent to the right triangle APD. Those two right triangles can join to each other according to angle, according to side similarity rule. Again, I repeat again, those two main triangles, triangle OAP and triangle PAD, can go into each other according to side rule. So I write it down. But before that, I will present to you a new rule that is actually rule number 1. After I present to you rule number 1, we prove that the two green right triangles can run to each other according to side rule. According to rule number 1, the lengths of two tangents from a common external point to a circle are equal. So what is the meaning of rule number 1? The meaning of rule number 1 is that if we have this circle and we have here this point P is an external point of this circle. Why point P is an external point? Because point P is not located inside the circle nor on the circle, but it is located outside of this circle. Therefore point P is defined as an external point of this circle. So if from the external point P will draw two tangents to this circle, so here the first tangent is this tangent, and the point of tangency of the first tangent with this circle is point A. And then we will draw a second tangent to this circle. And here the point of tangency of the second tangent with this circle is at point B. Then according to rule number 1, the lengths of two tangents, that is to say the length of the first tangent is PA, and the length of the second tangent is PB. And according to rule number 1, the lengths of two tangents from a common external point, that is to say from point P, because point P is a common external point, to a circle, to points A and B are equal. That is to say PA equals to PB according to rule number 1. I repeat again, the lengths of two tangents, that is to say PA and PB, from a common external point, that is to say from point P to a circle to points A and B are equal. That is to say PA PA equals to PB. So whenever you draw two tangents to a circle from a common external point to that circle, like in this drawing, then the length of the two tangents will be equal to each other. In this case, PA equals to PB. Okay, so we actually can implement rule number 1 in our drawing. Here we have the common external point, point A. From the common external point, point A, we have two tangents to the semicircle. The first tangent is tangent AO. Tangent AO is tangent to this semicircle at point O. Point O is the point of tangency. And the second tangent is tangent AD. Tangent AD is tangent to this semicircle at point D. Point D is the point of tangency. So, according to rule number 1, whenever you have two tangents to a circle or to a semicircle from a common external point, that is to say from point A to this circle or semicircle, then the lengths of those two tangents will be equal to each other. That is to say AO equals to AD according to rule number 1. I'll write it down. AO equals to AD according to rule number 1. Because we have from the common external point, point A, two tangents to this semicircle, tangent AO, and tangent AD, and according to rule number 1, the lengths of those two tangents must be equal to each other. That is to say, AO equals to AD. But according to what is given us in the question, AO equals to 6 units. Okay, so we can write down here that AO equals to 6 units. And from this equation, 6 equals to AO equals to AD, we will conclude that AD is also equals to 6 units. AD equals to 6 units. So we can write here that AD equals to 6 units. Here, this is AD, and it is equal to 6 units. I must emphasize that X is longer than AD. X equals to AC. Okay, X is longer than AD because X equals to AC. Okay, so at least right now we know that the length of line segment X is greater than 6 units. Okay, so in the next step we will prove that the two green right triangles can go into each other according to side rule. Side rule. So we will prove that the right triangle AOP, again right triangle AOP, congruent. This is the sign of congruent to the right triangle APD. This right triangle. So why those two triangles can go into each other? First of all, we just right now found out that AO equals to AD equals to 6 units, according to rule number 1. AO equals to AD equals to 6 units. Here AP is a common side, it belongs to both triangles, so AP equals to AP. It's a common side that belongs to both triangles. And finally, OP equals to PD equals to 3 units. This is the radius of the semicircle. OP equals to PD equals to 3 units. So actually, we proved that all sides of triangle AOP can go into all the sides of triangle APD. Therefore, triangle AOP can go into triangle APD according to side rule. Okay. And from the fact that those two green right triangles can go into each other, we will conclude hence that those two angles are equal to each other. That is to say, angle OAP is equal to this angle that is actually angle PAD. So those two angles, they are equal to each other according to the rule that corresponding angles in congruent triangles are equal to each other. Those two triangles can go into each other, therefore the two corresponding angles, that is to say those two angles that are defined as corresponding angles, will be equal to each other. For that reason, angle OAP equals to angle PAD. So if we define angle PAD as theta, then from this equation we derive angle OAP equals to angle PAD equals to theta. We will derive that angle OAP is also equals to theta. So here both those two angles, they are equal to theta. In the next step, we will focus on the right triangle AOP. In the right triangle AOP, this right green triangle AOP, we know that tangent theta equals to OP over OA. I will repeat again. In the right main triangle AOP, tangent theta equals to OP over OA. Okay. Here OP equals to 3 units and OA equals to 6 units. So in conclusion, I found out that tangent theta equals to 3 over 6. That is actually 1/2. Tangent theta equals to 1/2. In the next step, we will join points O and C together by a straight line. And I will present to you the law of cosines that I have already presented to you in the previous lecture, so I will do it shortly. So what is the law of cosines? As I have already mentioned before, The law of cosines is true in any triangle. So you can write down that in any triangle, if we have triangle ABC, that could be any triangle, this is triangle ABC. This is triangle ABC. We know that the length of side AB equals to A units. The length of side AC equals to B units. And the side BC equals to C units in its length. And we also know that the angle between side AB and side AC is alpha or theta. Let's call it theta, doesn't matter at all. Then, according to the law of cosines, we will get that C squared equals to A squared plus B squared minus 2 times A times B times cosine theta. Okay, I'll repeat again. C squared equals to A squared plus B squared minus 2 times AB times cosine theta. Now we will implement the law of cosines in triangle AOC. This triangle AOC. I will copy the triangle AOC in a new page and we will implement the law of cosines in this triangle AOC. Here we joined points O and C together by a straight line. What is the definition of line segment OC? Here, line segment OC starts from point O, that is the center of the quarter circle, and ends at point C, that is the point of the quarter circle itself. And this is exactly the definition of a radius. That is to say, OC equals to 6 units. Okay? OC is the radius of the quarter circle that is equal to 6 units. And here AC equals to x units according to what is given us in the question. That is the variable that we are looking for. That is the line segment that we are looking for. AC equals to x. And the angle between side OA and AC is theta plus theta, that is 2 theta. So I copied triangle AOC, this triangle, from the original drawing. So we will implement the law of cosines in this triangle, triangle AOC. according to the law of cosines, OC squared this will be equation number 1, OC squared equals to AO squared plus AC squared minus 2 times AO times AC times cosine 2 theta. Okay? Again, OC squared equals to AO squared plus AC squared minus 2 times AO times AC times cosine 2 theta. Okay? So here OC equals to 6, so OC squared is 6 squared, that is 36. And it is equal to AO squared. AO equals to 6, so AO squared is 6 squared, that is also 36. Plus AC squared. AC equals to X, so AC squared is X squared. Minus 2 times AO, that is 6, times AC, that is X, times cosine 2 theta. So here we have 36 on both sides of equation number 1, so 36 will get cancelled. And here we have, in this side of equation number 1, we have 0. It is equal to X squared. Minus 2 times 6 is minus 12, so here we have in total minus 12x cosine 2 theta. We will add 2x cosine 2 theta to this equation, equation number 1, and we will get that according to equation number 1, 12x cosine 2 theta equals to x squared. Here we will divide this equation number 1 by x. We should remember that x is the length of side AC. It is the variable that we are looking for, and it is a positive number. It can never be equal to 0, and that is the reason that we can divide equation number 1 by x, because it can never be equal to 0. It must be a positive number. As the length of a side, it must be a positive number. So we divide equation number 1 by x, and we get that according to equation number 1, 12 times cosine 2 theta equals to x squared, where x is x. So according to equation number 1, we found out that 12 times cosine 2 theta equals to x. So here in the next step, so we have to find out the value of cosine 2 theta, and then we find out x, that is the variable that we are looking for. So we have to find out the value of cosine 2 theta. Actually, we have trigonometric identity for cosine 2 theta according to the following trigonometric identity. Cosine 2 theta equals to 1 minus tangent square theta over 1 plus tangent square theta. I remind to you that we have already found out the value of tangent theta. Here we have already found out that tangent theta equals to 1/2. Okay, that is to say, we can substitute tangent theta in this trigonometric identity by 1/2. We will do it now, and we get that cosine 2 theta equals to 1 minus tangent theta is 1/2. I write it here. Tangent theta equals to 1/2. If tangent theta equals to 1/2, it means that tangent square theta will be equal to 1/2 square over 1 plus tangent square theta is 1/2 square. So here we have 1 minus half square is 1/4. Half square is 1/4, so I will substitute half square by 1/4 over 1 plus half square is 1/4. So in conclusion, we found out that cosine 2 theta equals to 1 minus 1/4 is 3/4 over 1 plus 1/4 is 5/4. Here we have 4 in the numerator and 4 in the denominator, so 4 will get cancelled, and we left only with 3/5, or 3/5. That is to say, we found out that cosine 2 theta equals to 3/5. 3/5. And we have a question number 1, that 12 times cosine 2 theta equals to x. Now we will substitute cosine 2 theta in equation number 1 by 3/5, and we get that 12 times cosine 2 theta is 3/5, and it is equal to x. So here 12 times 3 is 36 over 5 equals to x. That is to say, we found out that x, the line segment that we are looking for, equals to 7.2 units. Okay, I repeat again. Here x, the variable that we are looking for, equals to 7.2 units. We finished with the first method. In the next step, I will present to you how to find out the length of line segment AC that is equal to x according to the second method. In the second method, we will use in all the things that we have already found out in the first method. So this point equals to D, the point of tendency of AC in the semicircle is D. The center of the semicircle is point P. OP equals to 3 units, this is the radius of the semicircle. PV also equals to 3 units, it is also the radius of the semicircle. PD is also equals to 3 units, it is also the radius of the semicircle. And here we have already found out that triangle in this angle equals to 90 degrees. We have already found out the triangle, the right triangle AOP can go into the right triangle APD. Here AD equals to 6 units, of course. I repeat again, we have already found out that the right triangle AOP can go into the right triangle PAD according to side rule. I'll write it down. We have already found out that triangle AOP can go into triangle APD according to side rule. Those two angles are equal to theta. From the fact that those two triangles can go into each other, we conclude that angle OAP equals to angle PAD equals to theta. We already did it in the first method, so I will not repeat on it. And we'll continue. So all the things that I did now, that I did until now, we have already done in the first method. In the second method, we will do another construction. We will extend side AD until by straight line, and we will also extend side OB by straight line until it intersects with the extended side AC. So we extended line segment AC and line segment OB by a straight line until they intersect with each other at this point. This is the point of the intersections between the two straight lines. We define the point of intersection as point E. So by this construction, we actually created the right triangle AOE. Okay? We have the right triangle AOE that we created by the construction. In the right triangle AOE, AP is angle bisector of angle OAE. AP is angle bisector. And we have the angle bisector theorem. According to angle bisector theorem, angle bisector theorem. The angle bisector in a triangle divides the side that it hits in a ratio that is equal to the ratio of the angles legs. I will repeat on the angle bisector theorem again. According to angle bisector theorem, the angle bisector in a triangle divides the side that it hits in a ratio that is equal to the ratio of the angle's legs. Okay, so I'll explain what is the meaning of angle bisector theorem. So actually, if we have triangle ABC that could be any triangle, this is triangle ABC. AD is the angle bisector of angle BAC. Okay? It bisects, AD bisects angle BAC into two halves. Each half equals to half. So according to angle bisector theorem, the angle bisector in a triangle, that is to say AD is the angle bisector. I will write it here, angle bisector. So according to the angle bisector theorem, the angle bisector in a triangle, that is to say AD, line segment AD is the angle bisector, divides the side that it hits, that is to say it divides the side that it hits, line segment AD hits side BC. So it divides side BC in a ratio that is equal to the ratio of the angle's legs. The legs of the angle that is divided to two halves is AB and AC. Okay? So the ratio between the angles legs is AB over AC. Again, the ratio between the legs of the angle, that is angle divided into two halves, the legs of this angle is side AB and side AC. Those are the two legs of angle BAC. So, according to angle bisector theorem, the angle bisector in the triangle, that is to say AD, divides the side that it is, that is to say it divides side BC into two parts, BD and DC. And the ratio between those two parts is BD over DC. BD over DC. So, according to angle bisector theorem, the ratio between the angles legs, that is AB over AC, equals to the ratio that the angle bisector AD divides side BC, divides the side that it is, that is to say, divides side BC, and the angle bisector AD divides side BC in a ratio that is BD over DC, and that ratio equals to the ratio between the angle sides, that is to say, the angle legs, that is, and the ratio between the angle legs is AB over AC, because angle BAC is the angle that is divided into two halves. So AB over AC equals to BD over DC. Okay, this is angle bisector theorem, and we can implement angle bisector theorem in our drawing, because here we have triangle AOE. In triangle AOE, we have angle bisector, AP is angle bisector. So I copy triangle AOE in a new page, and we will implement the angle bisector theorem in triangle AOE. Okay. Triangle AOE is a right triangle. And AP is the angle bisector of angle OAE. So this is triangle AOE that I copied from the original drawing. This is triangle AOE that I copied from the original drawing. Side AO equals to 6 units according to what is given as the question. OB equals to 3 units, it is the radius of the semicircle. So, according to angle bisector theorem, we will get that the angle bisector AP divides the side that it is, that is to say, divides side OE in a ratio that is equal to OP over PE, and that ratio is equal to the ratio of the angles legs, and the angles legs is AO and OE, and the ratio between the angles legs is AO over AE. AO over AE. Again, according to angle bisector theorem, the ratio between the angles legs, that is to say, the angles legs is AO and AE, and the ratio between the angles legs is AO and over AE, and it is equal to the ratio that the angle bisector AP divides side OE. That is to say, it is equal to OP over PE. Okay, again, here, this will be equation number 1, AO over AE equals to OP over PE. According to angle bisector theorem, so here, AO equals to 6 units, AE is AE, and is equal to OP, that is 3 units, over PE. So in conclusion, we found out that according to equation number 1, 6 over AE equals to 3 over PE. We will divide this equation number 1 by 3 and we will multiply it by AE, and we will get that 6 over 3 equals to AE over PE. 6 over 3 is 2. So I write it down according to equation number 1, 2 equals to PE over AE. I multiply equation number 1 by AE. And we get that according to equation number 1, 2 times AE equals to PE. Here actually AE here 2 equals to PE. Here it is 6 over 2 equals to AE over PE. So here 6 equals to AE over PE. Then here I will multiply equation number 1 by PE, and we get that 2 times PE, according to equation number 1, 2 times PE equals to AE. Okay, 2 times PE equals to AE. So actually, AE is twice as large as PE. We define PE as A. PE equals to A. And then from equation number 1 we get that AE equals to 2PE, that is to say, and P equals to A, so A equals to 2A. So here we found out that PE equals to A, and AE equals to 2a, AE equals to 2a. In the next step, we'll focus on the right triangle AOE, and we'll implement on the Pythagoras theorem on the right triangle AOE. So in the right triangle AOE, we found out that A equals to 2A, and what is the length of OE? From the drawing, it is very easy to see that the length of side OE, it is equal to 3 plus PE. That is to say, it is equal to 3 plus PE, that is A. In conclusion, OE equals to 3 plus A. Okay, OE equals to 3 plus A. So this is the rectangle AOE. In the right triangle AOE, we implement the Pythagoras theorem by PT, is the abbreviation for Pythagoras theorem. The square of the hypotenuse equals to the sum of the squares of the perpendiculars. So here, the square of the hypotenuse is AE squared, equals to AO squared. The square of the hypotenuse equals to the sum of the squares of the perpendiculars. That is to say, it is equals to AO squared plus OE squared. So AE equals to 2A, therefore AE squared equals to 2A squared, and it is equal to AO squared. AO equals to 6, so AO squared is 6 squared, that is 36, plus OE squared. OE equals to 3 plus A, so OE squared is 3 plus A squared. We'll open the brackets on both sides of equation number 2, and we get that according to equation number 2, 2A squared is 4A squared, and it is equal to 36 plus 3 plus A squared. 3 plus A squared is 3 squared, that is 9, plus A squared plus 6A. Here, 36 plus 9 is 45. We'll subtract A squared from this equation, equation number 2. So A squared will get cancelled, then 4A squared minus A squared is 3A squared. So 3A squared equals to 45 plus 6A. We divide this equation number 2 by 3, and we get that according to equation number 2, a squared over 3 is a squared, 45 over 3 is 15, 6 over 3 is 2, so 6a over 3 is 2a. So in conclusion, I found out that according to equation number 2, a squared equals to 15 plus 2a. We subtract 15 and also 2a from this equation, equation number 2, and we get that according to equation number 2, a squared minus 2a minus 15 equals to 0. Here the coefficient a in the this quadratic equation, the coefficient a equals to 1. Write it here. The coefficient a equals to 1. The coefficient b equals to minus 2. And the coefficient c equals to minus 15. And the variable that we are looking for is a, so here x equals to a. And the general formula for solving a quadratic equation is x equals to minus b plus minus square root of b squared minus 4 times a times c over 2a. Here the variable that we are looking for in our specific quadratic equation is a, so x equals to a, so we'll put the data inside the formula for x and we find out the value of the values of a. So a equals to, x equals to a, so a equals to minus b equals to minus 2, so minus b is minus 2, that is 2, plus minus square root of b squared, b equals to minus 2, so minus 2 squared equals to 4, minus 4 times a is 1, times c is minus 15, over 2a. A is 1, so 2 times 1 is 2. So a equals to 2 plus minus, here minus 15 times minus 4 is 60, and 60 plus 4 is 64. So inside the root what is left is only 64 over 2. So I actually found out that a equals to 2 plus minus square root of 64 is 8 over 2. So here we will have two solutions that are possible for a. The first solution for a is a1 equals to 2 minus 8 over 2. 2 minus 8 is minus 6. Minus 6 over 2 is minus 3. So we found out that a1 equals to minus 3. But here a is the length of side PE, and A is a length, it must be a positive number. A is a length, therefore it must be a positive number. So it can never be equal to minus 3, that is a negative number, so we cancel this solution, and we're left only with the solution. The second solution, A2 equals to 2 plus 8 over 2. 2 plus 8 is 10, and 10 over 2 is 5. So we found out that A2 equals to 5. Okay, A2 equals to 5. So here we can write down that A equals to 5 units. And what is the length of line segment BE? From the drawing it is very easy to see that BE equals to PE minus PB. PE minus PB. PE minus PB equals to BE. So BE equals to PE, that is 5 units, minus PB, that is 3 units. So BE equals to 5 minus 3, that is 2. BE equals to 2 units. So we found out that BE equals to 2 units. And what is the length of CE? The length of line segment CE, from the drawing it is very easy to see that CE equals to AE minus AC. AE minus AC equals to CE. I repeat again. Here CE equals to AE minus AC. So AC equals to 2A, and A equals to 5, so 2A is 2 times 5, that is 10. So AE equals to 10 minus AC. AC is the line segment that we are looking for, that is equal to X, according to what is given in the question. So AC equals to X. So in conclusion, we found out that C equals to 10 minus X. So we can write here that C equals to 10 minus X. In the next step, we complete the quarter circle to a circle. So I completed the quarter circle to a circle, and we will extend line segment BO until it touches the circle. We will define the touching point of line segment BO if the circle is point M. So what is the value of line segment MO? MO is the radius of the circle, that is also the radius of the quarter circle. Why? Because line segment MO starts from point O, that is the center of the circle, and the center of the quarter circle also, and ends at point M, that is a point on the circle itself. And this is exactly the definition of a radius. That is to say, OM is the radius of the circle, that is also the radius of the quarter circle, that is to say, it is equal to 6 units. Okay, in the next step, I will present to you a new law, a new rule that is actually relates to two chords that intersect with each other outside the circle. Okay, so it will be actually rule number 3. According to rule number 3, if two chords intersect with each other outside the circle, if two chords intersect with each other outside the circle, that is to say externally, then the following equation is true. So if we have the external point P, and at this point P is the intersection point of the two chords. Okay, point P is the intersection point of the two chords. This is the first chord. This point is point B, this point is point A. This point is point B. And the second chord is this chord. As you can see, the two chords intersect with each other at point P. Point P is the intersection point of the two chords. That is to say, the two chords intersect with each other externally outside the circle. So this point is point C, and this point is point D. Then the following formula or equation is true, that PA times PB equals to PC times PD. So I repeat again on rule number 3. According to rule number 3, if two chords intersect with each other outside the circle, that is to say they intersect with each other externally, then the following equation is true, that PA times PB equals to PC times PD. Again, here, PA times PB equals to PC times PD. Okay? So we can implement rule number 3 in our drawing. In our drawing, the intersection point of chord AE and chord ME is at point E. Again, point E is the intersection point between those two chords that is actually outside the circle, as you can see. And therefore we can implement rule number 3. Because of the fact that point E is outside the circle, we can implement rule number 3. Because rule number 3 relates to the two chords that intersect with each other externally outside the circle. So according to rule number 3, we get here that EC times EA equals to EB times EM. Again, according to rule number 3, we get that EC times EA equals to EB times EM. I repeat again, according to rule number 3, EC times CA equals to EB times CM. EC times EA equals to EB times CM. Okay? EC equals to 10 minus X. EA equals to 10. EA equals to 10. And it is equal to EB. EB equals to 2 units. And EM equals to 6 plus 3 plus 3, that is 12, plus 2, that is 14. EM equals to 14. So in conclusion, we found out that EC times CA equals to EB times CM, and it is equal to 10 minus X times 10, that is equal to 2 times 14. 2 times 14 is 28, and it is equal to 10 times 10 minus X. Here we will divide this equation by 10, and we get that 10 minus X equals to 28 over 10 is 2.8. Here we will add X to this equation and subtract 2.8, and we get that X equals to 10 minus 2.8, that is 7.2. So in conclusion, we found out that X equals to 7.2 units. Okay, here X equals to 7.2 units. X, that is equal to AC, equals to 7.2 units according to the second method also. So in the next step, I will summarize the lecture. We'll start with the first method, of course. So I repeat on the question here. We have a semicircle inside the quarter circle. AO equals to 6 units, and we want to find out the length of side AC that is equal to x. So we defined the point of tangency of tangent AC with this semicircle as point D. We defined the center of this semicircle as point P. And here OA is the radius of the quarter circle because of the fact that line segment OA starts from the center of the quarter circle, that is to say from point O, and ends at point A, that is a point on the quarter circle itself. And this is exactly the definition of a radius. That is to say, OA is the radius of this quarter circle that is equal to 6 units. For the same reason, exactly OB is also the radius of the quarter circle, that is to say it is equal to 6 units. And this angle equals to 90 degrees. Angle AOB equals to 90 degrees because of the fact that this is a quarter circle. This angle AOB must be equal to 90 degrees. Then we joined points P and O together, P and D together by a straight line. PD equals to OP equals to PB. All are the radii of the semicircle. That is because of the fact that they start from the center of the semicircle, that is to say from point B, and at any point on the semicircle itself. And this is exactly the definition of a radius of a circle or semicircle. And because of the fact that the diameter of this semicircle equals to 6 units, therefore the radius must be equal to half of it. That is to say, the radius of the semicircle equals to 6 over 2, that is 3 units. Then I presented to you rule number 1. According to rule number 1, the lengths of two tangents from a common external point to a circle are equal. So here we have this circle, and we have point P that is external point in relation to this circle. So we draw two tangents to this circle. The first tangent is tangent PA, and the second tangent is tangent PB. And according to rule number 1, the lengths of two tangents, that is to say PA and PB, PA is the length of the first tangent, PB is the length of the second tangent. So the lengths of two tangents from a common external point, that is to say from point B, that is a common external point, to a circle, to points A and B, are equal. That is to say PA equals to PB according to rule number 1. So whenever you draw two tangents to a circle from a common external point to any circle, then the lengths of those two tangents will be equal to each other. In this case, PA equals to PB. Okay, so we can implement rule number 1 in our drawing. Why? Because in our drawing we have the common external point, point A. Point A is an external point in relation to the semicircle, and from the common external point, point A, we have the first tangent is tangent AO, that is tangent to this semicircle is point O. Point O is the point of tangency, and we have the second tangent that is tangent AD. Tangent AD is tangent to this circle as point D. Point D is the point of tangency. Then according to rule number 1, the lengths of those two tangents must be equal to each other. That is to say AO equals to AD according to rule number 1. Okay, AO equals to AD according to rule number 1. But according to what is given in the question, AO equals to 6 units. So we can write here that AO equals to 6 units. And from this equation 6 equals to AO equals to AD, we will derive that AD is also equals to 6 units. Here AD equals to 6 units also. And then we actually proved that the two green line triangles, triangle AOP, is congruent to triangle APO according to side rule. So why those two green triangles congruent to each other? First of all, we know that we just right now found out that AO equals to AD equals to 6 units. In addition, AP is the common side that belongs to both triangles, so AP equals to itself, and OP equals to PD equals to 3 units. It is the radii of the semicircle, therefore they are equal to each other. So we prove that those two right green triangles congruent to each other according to side rule. Triangle AOP congruent to triangle APD according to side rule. And from the fact that those two right green triangles congruent to each other, we conclude that those two angles are equal to each other, according to the rule that corresponding angles in congruent triangles are equal to each other. So angle OAP equals to angle PAD equals to, so if we define one angle as theta, then the other angle must be also equal to theta because of the fact that those two angles are equal to each other, so both those two angles are equal to theta. Then we focus on the right triangle AOP, the right green triangle AOP times theta equals to PO over OA. In the green triangle AOP times theta equals to OP over OA. Because theta equals to OP over OA. OP equals to 3 units, OA equals to 6 units. So triangle theta equals to 3 over 6, that is 1 over 2. So in conclusion, we found out that triangle theta equals to 1/2. Okay? Then I presented to you the law of cosines, and we implemented the law of cosines in triangle AOC after we connected the joined together points O and C together. We implemented the law of cosines in this triangle AOC. So what is the law of cosines? The law of cosines is true in any circles, in any triangle. So here in any triangle, if you have triangle ABC, that could be any triangle, side AB equals to A units, side AC equals to B units, and side BC equals to C units instead. And the angle between side AB and side AC is theta. Then according to the law of cosines, C square equals to A square plus B square minus 2 times AB times cosine theta. Okay, again C square equals to A square plus B square minus 2AB times cosine theta. We implemented the law of cosines in our triangle AOC, so I copied triangle AOC. This is not a right triangle. In a new page, and we implemented the law of cosines in the right triangle, in triangle AOC. It is not a right triangle. Okay. Here in triangle AOC, according to the law of cosines, OC square equals to AO square plus AC square minus 2 times AO times AC times cosine 2 theta. Again, OC square equals to AO square plus AC square minus 2 times AO times AC times cosine 2 theta. OC equals to 6, so OC square is 6 squared is 36, and it is equal to AO square. AO is 6, so AO square is 6 squared is 36. And plus AO square. AO equals to, it is actually AC square. AC equals to X, so AC square is X square minus 2 times AO, that is 6, times AC, that is X, times cosine 2 theta. So we have 36 on both sides of the equation, so 36 will get cancelled, and we left only here with 0, that is equal to X square. 2 times minus 2 times 6 is minus 12, so this expression equals in conclusion to minus 12 times X times cosine 2 theta. We added minus 12x cosine 2 theta to this equation and found out that 12x times cosine 2 theta equals to x squared. We divided this equation number 1 by x and found out that cosine 12 times cosine 2 theta equals to x. Okay, x equals to 12 times cosine 2 theta. So the only thing that is left to do is to find out the value of cosine 2 theta. And we actually have trigonometric identity for cosine 2 theta. According to this trigonometric identity, cosine 2 theta equals to 1 minus tangent square theta over 1 plus tangent square theta. And we already found out that tangent theta equals to 1 half. So we can substitute tangent theta by 1 half. We did it and we got here that cosine 2 theta equals to 1 minus tangent square theta. Tangent theta equals to 1 half. Tangent square theta will be equal to 1 half squared, that is 1 quarter, over 1 plus tangent square theta. Tangent square theta is 1 half squared, that is 1 quarter. So in conclusion, we found out that cosine 2 theta equals to 1 minus 1 quarter over 1 plus 1 quarter. 1 minus 1 quarter is 3 quarters, and 1 plus 1 quarter is 5 quarters. So here we have 4 on both sides in the numerator and 4 in the denominator, so 4 will get cancelled, and we left only with the expression that cosine 2 theta equals to 3/5. Cosine 2 theta equals to 3/5. And according to equation number 1, we have already found out that 12 times cosine 2 theta equals to x. So we substitute cosine 2 theta by 3/5. We did it and we got that according to equation number 1, 12 times cosine 2 theta is 3/5 equals to x. So here 12 times 3 is 36 and 36 over 5 is x. So in conclusion, found out that x equals to 36 over 5, or in terms of numbers, it is equals to 7.2 units. Here, x equals to 7.2 units. X that is equal to AC equals to 7.2 units. Okay, we finished with the first method. In the next step, I present it to you. In the next step, I will present to you how we found out the value of line segment x according to the second method. In the second method, we used all the things that we already found out in the first method. We already found out that triangle AOP can go into triangle AOC according to side rule. Again, triangle AOP can go into triangle APD according to side rule. And from the fact that those two triangles can go into each other, we conclude that those two angles they are equal to each other according to the rule that corresponding angles in congruent triangles are equal to each other. So if one angle equals to theta, then the other angle must be equal to theta. So those two angles, they are both equal to theta according to our definition. Then we made another construction in the second method. We extended ADC, line segment ADC by straight line, and we also extended line segment OB by straight line until they intersect with each other at point E. Point E is the intersection point of the extended line segment AC and the extended line segment OB. In this way, we get the triangle AOE, the right triangle AOE, and here AP is the angle bisector of triangle AOP. Why? Because it bisects angle OAP into two halves. the first half is theta, and the second half is also theta. Then I presented to you the angle bisector theorem. According to angle bisector theorem, the angle bisector in a triangle divides the side that it hits in a ratio that is equal to the ratio of the angle's legs. So here we have this triangle ABC, that could be any triangle. Here AD, line segment AD, is angle bisector. Why? Because it bisects angle BAC into two halves. The first half is theta, and the second half is also theta. So according to angle bisector theorem, the angle bisector AD divides the side that it hits. Angle bisector AD hits side BC, and it divides this into two parts, BD and DC, and the ratio between those two parts, that is to say BD over DC, equals to the ratio between the angle's legs, and the angle's legs are AB and AC, and the ratio between the angle's legs is AB over AC. So AB over AC will be equal to BD over DC. Again, the angle bisector in a triangle, that is to say AD, divides the side that it hits. It hits side BC and divides it into two parts. The first part is BD and the second part is DC. And the ratio between those two parts is BD over DC. And that ratio equals to the ratio of the angle's legs. The angle's legs is AB and AC. The ratio between the angle's legs is AB over AC. That is to say AB over AC equals to BD over DC. Okay, so this is the angle bisector theorem, and we can implement the angle bisector theorem in our drawing. Why? Because in our drawing we have triangle, the right triangle AOE. This is triangle AOE, the right triangle, and the angle bisector is AP. The angle bisector AP divides the side that it is in a ratio that is OP over PE, and that ratio equals to the ratio of the angle's legs. The angle's legs is AO and AE, and the ratio between the angle's legs is AO over AE. That ratio equals to OP over PE. Is the ratio that the angle bisector AP divides the side that it is, that is OE. It is side OE at point P and divides it into two parts, and the ratio between those two parts is OP over PE, and is equal to the ratio between the angle's legs, that is AO over AE. Okay, so here AO equals to 6 units, AE is AE, OP equals to 3 units, it is the radius of the semicircle over PE. We multiplied equation number 1 by here. We divided equation number 1 by 3 and we multiplied by AE, and we found out that 6 over 3 equals to AE over PE. 6 over 3 is 2. So in conclusion, 2 equals to AE over PE. We multiplied the equation number 1 by PE, and we got that 2 times PE equals to AE. So AE equals to 2 times PE. We defined PE as A. Here, PE equals to A according to our definition. So if PE equals to A, then according to equation number 1, we get that AE equals to 2 times PE, that is A, that is to say AE equals to 2A. So according to equation number 1, AE equals to 2A. So you can find out that AE, side A equals to 2A, and PE equals to A. Now we can implement the Pythagoras theorem on the same right triangle, triangle AOE. So I complete the right triangle, triangle AOE. Here PE equals to 3 OE, side OE equals to OP plus PE. Okay? And OP equals to 3 units and P equals to A. So in conclusion, OE equals to 3 plus A. Okay? OE equals to 3 plus A. AO equals to 6. This is given as the question. We just right now found out that A equals to 2A. This is a right triangle, this is equals to 90 degrees. So we implemented the Pythagoras theorem on the right triangle, triangle AOE. According to the Pythagoras theorem, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. That is to say, AE square equals to AO square plus OE square. AE equals to 2A. So AE square is 2A square, and it is equal to AO square. AO is 6, so AO square is 6 square, this is 36, plus OE square. OE equals to 3 plus A, so OE square equals to 3 plus A square. We open the brackets on both sides of this equation, equation number 2, and found out that 2A square equals to 4A square, and it is equals to 36 plus 3 plus A square equals to 3 squared, that is 9 plus A square plus 6A. So here 36 plus 9 is 45, and we also subtracted A square from equation number 2. 3A square minus A square, 4A square minus A square is 3A square. A square minus A square is 0. So in this side of the equation, what is left is only 45 plus 6A. And in this side of the equation, what is left is 3A squared. So in conclusion, according to equation number 2, 3A squared equals to 45 plus 6A. We divided equation number 2 by 3, and we got that 3A squared over 3 equals to A squared. 45 over 3 is 15, and 6A over 2 is 2A. So in conclusion, according to equation number 2, we found out that A squared equals to 15 plus 2A. Okay? Here we subtracted 15 and also 2A from this equation, equation number 2, and found out that according to equation number 2, A squared minus 2A minus 15 equals to 0. So we have here a quadratic equation. In this quadratic equation, the coefficient A equals to 1, the coefficient B equals to minus 2, and the coefficient C equals to minus 15, and the variable that we are looking for is A. So, and the formula for finding out the value of the variable of the quadratic equation is x equals to minus b plus minus square root of b squared minus 4 times ac over 2a. Here, x equals to minus b, b equals to minus 2, so minus b is minus 2, that is 2, plus minus b squared is minus 2 squared, that is 4, minus 4 times a is 1, times c is minus 15. Over 2a, a is 1, so 2 times 1 is 2, so in conclusion we found out that a equals to 2 plus minus square root of, here, minus 4 times minus 15 is plus 60, and 60 plus 4 is 64. So inside the root we left only with 64 over 2 equals to 2 plus minus square root of 64 over 2. The square root of 64 is 8. So in conclusion we found out that a equals to 2 plus minus 8 over 2. We have two solutions that are possible. The first solution is a equals to 2 minus 8 over 2. 2 minus 8 is minus 6, and minus 6 over 2 is minus 3. So we found out that a equals to minus 3. But because of the fact that a is the length of side PE, a is a length, it must be a positive number. A is a length, it must be a positive number, so it can never be equal to a negative number. So this solution is the correct solution. We cancel this solution, and we left only with the second solution. that a equals to 2 plus 8 over 2. 2 plus 8 is 10 and 10 over 2 is 5. So if we know that a equals to 5, so here we know that a equals to 5, p equals to a equals to 5. And what is the length of BE? From the drawing it is very easy to see that PE minus PB equals to BE. Again here, PE minus PB equals to BE, PE equals to A, that is 5. PB, it is the radius of the semicircle, that is 3. So in conclusion, PB equals to 5 minus 3, that is 2. So this line segment BE equals to 2 units. Likewise, we found out the value of CE. Here CE equals to AE minus AC. Again, AE minus AC equals to CE. Again, CE equals to AE minus AC. AE equals to 10, AC equals to X. So in conclusion, we found out that C equals to 10 minus X. C equals to 10 minus X. Then I presented to you a new rule, that is rule number 3. According to rule number 3, if two chords intersect with each other outside the circle, that is to say externally, then the following equation is true, that PA times PB equals to PC times PD. Okay, I'll repeat again. We have this circle and we have the external point, point P. From the external point, point P, we actually have point P is the intersection point of those two chords. And whenever you have two chords in a circle that intersects with each other externally, outside the circle, then the following formula is true, that PA times PB equals to PC times PD. Again, PA times PB equals to PC times PD. So implemented rule number 3 in our drawing. In our drawing, we have the external point, point E. In this external point, point P, we have chord AE and chord MB that intersects with each other. But first of all, actually, we completed the quarter circle to a circle, and we extended side BO by straight line until it touches the circle with point M. Point M is the touching point of the extended line segment OB in the circle. What is MO? O is the center of the circle and the center of the quarter circle. M is a point on the quarter circle, on the circle itself. And this is definition, exactly the definition of a radius. So M equals to the radius of the quarter circle, that is also the radius of the circle, that is to say it is equal to 6 units. So we have here chord EM and chord AE that intersect each other with each other externally at point E outside the circle. Point E is the intersection point of those two chords, and according to rule number 3, we get that EC times EA equals to EB times EM. Okay. EC times EA equals to EB times EM. According to rule number 3, EC equals to 10 minus X, EA equals to 10 units, EB equals to 2 units, and EM equals to 6 plus 3 plus 3, that is 12, plus 2 is 14. So in conclusion, EM equals to 14 units. So in conclusion, I found out that 10 minus X times 10 equals to 2 times 14, that is 28, or 10 times 10 minus X equals to 28. We divided this equation by 10 and we found out that 10 minus x equals to 28 over 10 is 2.8. We added x to this equation and we subtracted 2.8, and in conclusion we found out that x equals to 10 minus 2.8, that is to say it is equal to 7.2 units. So here the length of line segment AC that is equal to x, it is equal to 7.2 units. Okay, so in both methods we arrive to the same answer for the value of line segment x, that is to say it is equal to 7.2 units. Okay, thank you very much.